All right, welcome to another video in the STEM series. Please check out the STEM Club. All right, we do Arduino projects, radio broadcasting systems, and all sorts of fun electronic projects. All right, so the topic today will be electricity, and we'll be covering concepts in the CAPE syllabus, and we'll be going through the syllabus step by step in this series. There are two types of charges. All right. So this should be very familiar from CSEC. There are two types of charges. There are positive and negative charges. So examples of positive charges includes protons, magnesium 2 plus ions, and a sodium plus ion. All right, this you'll more come across this in chemistry, and protons you will come across the proton more when you do nuclear physics later down. Examples of negative charges include the electron, the chloride minus ion, the fluoride minus ion. This again you come across more in chemistry. The electron will interface with a lot more in our physics classes. Alright, so those are the two types of charges, positive and negative charges. The SI unit of charge is the coulomb. Alright, and of course that is named in honor of Mr. Coulomb, who did some works on the force between electric charges, alright, sometime in the 18th century. Now Q is equal to I times T, where Q stands for the quantity of charge present at a certain point in a circuit, or the quantity of charge flowing past a point. I stands for current, and T stands for time. Now CAPE will want this definition. 1 coulomb is equal to 1 amp multiplied by 1 second. Now a coulomb, 1 coulomb is equal to 1 amp second. This, you'll normally see this in the multiple choice of your CAPE exam, and CAPE will want you to be able to state this in words. So 1 coulomb is equal to 1 amp times 1 second. In words, you obtain 1 coulomb of charge when a current of 1 amp flows for 1 second. Now electric current is a flow of charged particles. Alright, and charged particles normally in a wire are normally electrons. So a moving electron is considered to be an electric current. Even when positive charges move, that's an electric current. Now when you have an ionic solution, in an ionic solution, what you have is mobile ions, and mobile ions can carry an electric current. In a wire, you have electrons that are moving, and the electrons are responsible for carrying the current. Alright, so sometime CAPE, alright, will ask you to say what charged particles is carrying current in a particular situation, and what charged particles is carrying current in a different situation. For example, electrons carry current in the wires, alright, and mobile ions carry current in a solution. Alright, so that's the idea. Alright, so let's moving on. So we come to the symbol for the electric current is I. There are two types of current that we'll interface with at this level, with DC current and AC current. So these are the two types of current in general. DC current comes from batteries and cells and the DC generator. AC current mainly comes from AC generator, and this AC current is normally current that JPS supplies. Alright, and in our part of the world, we're normally supplied current at 50 hertz. That means that we have 50 waves generated per second, or we have 50 oscillations per second, or 50 cycles per second. Alright, more about that when we do AC, since AC is also on the Physics Unit 2 syllabus. Alright, so this is DC current, direct current, and AC current, which stands for alternating current. Now we come to the concept of potential difference. Now in physics and in electricity, in order for current to flow, there must be what we call a potential difference. So in order for current to move from one place to the next in a circuit, there must be a difference in potential. If there is no difference in potential, current will never ever flow. Alright, so that is one general rule of thumb. So anywhere at all we observe moving charges, there must be a potential difference. What we'll see later on is that once there's a potential difference, there's also an electric field. So we're going to be doing fields in detail, but I'm just telling you now, so that once they have a potential difference, there has to be an electric field. Once there's an electric field, there will be force on each electron in the wire. And once there's a force, there will be motion in accordance with Newton's second law. that you'd have studied before in CSEC and in CAPE Unit 1. Alright, and also please stay tuned to the CAPE Unit 1 series. So for current to flow in a circuit, there must be a potential difference, a difference in potential. So in this first example, this end is at plus 5 volts of potential, this end is at 0 volts of potential. So since clearly there is a potential difference, current will flow. And current flows from high potential to low potential. Alright, also here, this is at plus 10 volts of potential. Here is at negative 2 volts of potential. Here again, there is a difference in potential, so current will flow, and that is the direction in which current will flow. Conventional current I will flow from the positive terminal to the negative terminal, or from high potential to low potential. That is the direction in which conventional current flow. There's a next flow in circuits called electron flow. Electrons flow in the opposite direction to conventional current flow. Alright, so some more examples here. Here again, we have 2 points. These 2 points are at the same electrical potential, 0 volts and 0 volts. Normally in physics, we call 0 volts ground or earth. So when 2 points are at the same electrical potential, no current flows. For another example, one end is at plus 15 volts of potential, the next one is at plus 5 volts of potential. What happens is that conventional current flows from high potential to low potential. So that is how conventional current flows. It flows from high potential to low potential. Alright, so now we come to Ohm's law. This law stands for George Ohm's law. And he says that when you apply a potential difference across a wire, the potential difference is directly proportional to the size of the current that will flow, provided that the temperature is held constant. So when a potential difference is applied across a conductor, alright, that potential difference is directly proportional to the current that will flow, provided that temperature is constant. This is a nice and easy way to remember Ohm's law. V is directly proportional to I, provided temperature remains constant. So long as the temperature is constant, this relationship is forever true. So if I double my voltage, my current should also double. If I triple my voltage, my current should also triple. If I quadruple my voltage, my current should also quadruple. So voltage is directly proportional to current. Now, voltage and potential difference is one and the same thing. So we'll be using those two terms interchangeably. So voltage and current, voltage and potential difference, is one and the same thing. So we'll be using those things interchangeably. Alright, so this is a mathematical form of Ohm's law. So you can write it out in words that the potential difference across a conductor is directly proportional to the current that will flow, provided that the temperature remains constant. Ohm's law also requires other physical constants or quantities to be constant, like the length of the wire, the stress on the wire, etc. But this is the form that you'll normally see it in. So what this therefore means is that V is equal to I times some constant R, where R stands for resistance. Alright, and resistance is normally the opposition to the flow of current, and we'll come to that in more detail. I stands for the current flowing, and the SI unit of current is amps, and V stands for voltage. So the V here is voltage, I stands for current, and R is resistance. This is normally the first form you'll see the equation in. If I want to find current, however, the current I is equal to V divided by R. Alright, so once I know the voltage and I know the resistance, I can calculate the current flowing in my circuit. Also, if I want to calculate my resistance R is equal to voltage divided by current. So once I have my voltage and once I know current, I can calculate my resistance. Now, what potential difference is? In formula, potential difference is the work done per unit charge to bring a charge from one place in a circuit to a next place in a circuit. So that's what potential difference is. It's the work done per unit charge to move a charge from one place to another place in a circuit. That is what potential difference is, or voltage. the formula V, which stands for potential difference, is equal to W over Q, where W is the work done, all right, and Q stands for charge, and that is the definition of potential difference. R is equal to V over I, and so what we can do is that we can start from the formula and then we can come up with a definition for the ohm. Cape want this definition, so Cape want the definition for potential difference, Cape want the definition for resistance, and also the unit of resistance, which is the ohm. In words, what this means is that you will obtain 1 ohm of resistance when a potential difference of 1 volt will cause a current of 1 amp to flow in your circuit. So if you start with your formula, you can move from the formula to the SI units, and from the SI unit you can state the definition of the quantity in words. The quantity here that we want to define is the ohm. 1 ohm is equal to 1 volt per amp, which in words mean that 1 ohm of resistance is obtained when a voltage of 1 amp causes a current of, when a voltage of 1 volt causes a current of 1 amp to flow in a circuit. Alright, so 1 ohm is obtained when a voltage of 1 volt causes a current of 1 amp to flow in a circuit. Alright, so that is so far. So next, we go deeper, and we come to the characteristic curve that Capes wants. So IV curves are normally characteristic curves. Characteristic curves are like DNA. I can use a characteristic curve to tell the type of circuit component I have. So when I have a straight line in particular, I know that I have a conductor. And there are many things that are conductors. All metals tend to be good conductors. Alright, and good conductors tend to give you a straight line when you plot current on the y-axis versus voltage. For the filament lamp, however, from this point here to a certain point up here, you have a straight line. So from here to here, it is ohmic. And ohmic means that you're obeying Ohm's law, but part of the curve is non-ohmic. So this part of the curve is not obeying Ohm's law. What Ohm's law says is that voltage must always be directly proportional to current. Right here, there's no proportionality right here. There's no direct proportionality right here. But from here to here, alright, so let's put some, alright, definite points to it. So between the points say O and the point say here, so between OA, so between OA, this part is ohmic, but between A and this point, alright, so let's give this point a name, call this point B. So between AB is non-ohmic. Remember, ohmic means that you're obeying Ohm's law. Non-ohmic, you're not obeying Ohm's law. So if we're not obeying Ohm's law, it means that V is not proportional to I. Alright, so that's the concept so far. Alright, so next we come to what exactly a filament lamp is. So just to stretch your imagination a bit, or you will be very familiar with this because these are normally a 60 and 100 watt bulbs that you normally use. This is very inefficient. This type of bulb converts 90% of the electrical energy to heat energy, which is what you don't want. Only 10% of the electrical energy is converted to light, so that's very, very inefficient. So this creates a lot of heat. When you normally switch on a bulb like this, within a very short time, the glass gets super hot. Alright, and of course that heat, we're not using it, so we call that wasted energy. However, this is a filament lamp, and inside the filament lamp you normally have nitrogen. Alright, so inside your filament lamp you normally have nitrogen or an inert gas. Alright, so inside your filament lamp, so this is my filament. Alright, the filament is normally made of a material called tungsten, and this part here is your bayonet cap. This is normally for your electrical contacts or electrical connections, and then over here there is a glass bulb. Alright, so that is for your filament so far. So we're coming to the rest of the IV characteristic curves, and this IV characteristic curve, this is the characteristic curve of a diode. So for a diode allows current to flow in one direction and one direction only. So when current is conducting, or when a diode allows current to conduct, the diode is said to be in forward bias. When a diode does not allow current to pass, the diode is said to be in what we call reverse bias. So that's to make you see that word R. Just to let you see this R word, that's reverse bias on this side and forward bias on this side. We'll be diving into the diodes in more detail in later topics. This 0.7 here is very specific. This is normally called a switch-on voltage. So the diode is a semiconductor. So the diode only conducts under certain circumstances. When the voltage is bigger than 0.7 on the diode, then the diode conducts lots of current. When the voltage is smaller than 0.7, there is very little current flow that you can get from the diode. So that is why the diode is a semiconductor. It only conducts under certain circumstances or certain conditions, to be very specific to science. Alright, so more about diodes later. This is the IV characteristic curve of a thermistor. So current is on the y-axis again, voltage is on the x-axis, and this is a thermistor. Now a thermistor really is a transducer. And a transducer is a device that is used to convert energy from one form to another, mainly from electrical energy into other forms of energy, or from other forms of energy into electrical energy. So the thermistor is a type of resistor, but this is a heat dependent resistor. So the value of the resistance changes as the heat on the thermistor changes. So this can behave like a heat sensor in each circuits, and we're going to be using the thermistor, the LDRs, in lots of our Arduino projects. So stay tuned to the STEM program and the STEM club. Follow us on YouTube. The next concept is the concept of resistivity. Now R is equal to rho L divided by A. Here R stands for resistance, and the SI unit of resistance is ohms. Rho stands for resistivity, and the SI unit of resistivity is the ohm meter. And L stands for the length of the wire in meters. From this formula, we see that resistance is directly related to resistivity. Resistivity is just the resistance for every 1 meter of wire, as we'll see shortly. And also resistance is related to the length of the wire. And this is a very important concept. What this means is that the longer the wire, the greater the resistance. So as the length of the wire increases, the resistance on the material also increases. Resistance, however, is inversely proportional to the cross-sectional area. Alright, so that's for that. Alright, so moving on. So we've just said this a while ago. Resistivity is the resistance for every 1 meter of wire. Resistance, however, is the opposition to the flow of current. So this is the definition of what resistance is. So resistance is the opposition to the flow of current. So far we have introduced a few formulas. Alright, the first formula we introduced was Q is equal to IT. Let's use that to solve some simple problems, fairly simple problems. Because what we want to do in example 1 is that we want to calculate the steady current that will flow when a charge of 40 coulomb flows for 4 seconds. So what that means is that we're going to extract the information. We have a charge of 40 coulombs and it flows for a time of 4 seconds. What we have said so far is that once charge is moving, we know that we have electric current. So once we have moving charge, we have electric current. We have a formula that relates charge, current, and time. And this formula right here is Q is equal to I times T. So if I want to calculate my current, I need to know the charge and I need to know the time. So what this means is that I'll transpose I, so I is equal to Q over T. So my charge is 40 coulombs, the time is 10 seconds, so I is equal to Q over T, which is 40 coulombs over 4, and I will get 10 coulombs per second. What this graph showed you earlier on is that this is steady current. This is what we call direct current. In real life, the line is not as steady as this. There is normally a little ripple effect, and this is more like for an ideal ideology or a theoretical ideology. This completely flat line, normally there is a little ripple on the line, but this is what we call steady DC, and DC stands for direct current. So the result of that simple calculation, just to come back to that, is that I equal 10 amps. But remember that 1 amp is equal to 1 coulomb per second. Alright, so for example 2 now, in example 2, we have a cylinder of length 12 meters. Alright, and the cylinder has a resistivity of 1.7 times 10 to the negative 8 ohm meters, and the cross-sectional area of the cylinder is 0.4 centimeters squared. What they want us to do is to calculate the resistance of this material given the length, given the resistivity, and given A. What we know is that there is a formula that relates R to the area, resistivity, and L, and that formula is R is equal to rho L over A. Here R stands for resistance, and the SI unit of resistance is ohms. Rho stands for resistivity, and the SI unit of resistivity is ohm meter. L stands for length, and A stands for area. So just plugging in the numbers, I will have 1.7 times 10 to the negative 8 times 12. This 0.4 centimeters squared should be converted to meters squared, because we have to work in SI units. And what that means is that our resistance R should come down to about this. You can try this in your calculator and see if you get this answer. So R is equal to 0.0051 ohm. For part B of this is that if we now apply a potential difference across that piece of cylinder that has a resistance of 0.051 ohms, what we will get is that we can be able now to calculate the current. So once we have resistance and we have a potential difference, current will flow. And that was what we said earlier on, that once there is a potential difference across any conductor, current will flow. We know that conventional current will flow from high potential to low potential. This long part of the wire is high potential, which is the positive part, and this is low potential. So conventional current will flow from the positive terminal all the way around to the negative terminal. So putting in the numbers, I is equal to V is 24 volts, and that goes in the numerator, and the resistance is 0.0051, and so this is what we get for our result. Alright, so those are for our two examples thus far. And then it's time we go on to our third example. So in the third example, it is said that a charge of 40 microcoulomb flows for a time of 5 milliseconds. We're supposed to calculate the steady current that will flow. If the current is steady, it means that we're calculating DC current. And then what will happen is that we'll just plug in the numbers. We'll use the formula I equal Q over T. We know the charge, so it's 40 times 10 to the negative 6 coulombs. And the time is 5 times 10 to the negative 3 seconds. Common M here stands for milli, and the SI unit of milli is 10 to the negative 3. Micro is 10 to the negative 6. That is the reason why 10 to the negative 6 come here, because micro is 10 to the negative 6 and milli is 10 to the negative 3. So dividing now, I'm now in SI units. I will get I is equal to 8 times 10 to the negative 3 coulombs per second. But as we have said before, a coulomb per second is equal to an amp. 1 coulomb per second is equal to 1 amp. And so I is equal to 8 times 10 to the negative 3 coulombs per amp. This they like to give you in the multiple choices. Alright, questions for Cape. So okay, so that is the first class on electricity. The next topic that we'll go on to is the mechanism of conduction in metals. So if you have missed the first 2 weeks of classes that I teach, Saturday classes that I teach, you can follow me on YouTube and you will pretty much get back what we did for the first 2 to 3 weeks of classes. So what's to come is the mechanism of conduction in metals. We're going to be talking about drift velocity and the origin of resistance and heat. Next to come in the series is the derivation of the formula I equal NAVE, that is for current in a narrow channel. And also next we'll go on to circuits. So we'll go on to series circuits and parallel circuits. And also after series and parallel circuits, we'll have to derive the formulas for resistors in series, derive the formula for resistors in parallel for Cape. Cape requires that. And the next thing that we'll go on to after that is Kirchhoff laws, or some persons say Kirchhoff laws, some Europeans say Kirchhoff laws. So we'll go on to Kirchhoff laws. Alright, so Kirchhoff have 2 laws, and we'll state the laws and apply them to solve some problems. And so that is the first set of things that we'll do in the electricity block. So until then, take care, and remember to subscribe to the STEM Club, and also visit us, all right, at our location that was shown in the poster before. All right, if you're in Jamaica, or just follow me on YouTube, send me post, all right, stuff like that, send me your comments. All right, bye bye. Until now, this is all about just creating persons, little geniuses, persons who love knowledge. All right, so take care until then. Bye bye.